All right, next up, we're going to hit on diffusion and effusion. And so we'll see that even when gases are both behaving ideally, there are instances where they're going to behave differently. So even if both of these gases are ideal gases, they can still act differently. So before we talk about this, let's just cover mean free path. Not that important, but basically the mean free path is the average distance a molecule moves before a collision. Before a collision. Cool. So molecules, of gas are bouncing around. So mean free path is how far can they travel before they hit something. And then diffusion, effusion are kind of the same thing, pretty similar. So diffusion, you think about diffusing, spreading out, and basically diffusion is movement from high to low concentration. Cool. And so what's true about gases, gases always spread as much as possible, right? They take the volume of the container. Cool. So that's diffusion. Effusion is very similar, just slightly different. Effusion is diffusion through a small hole. So for example, if you have kind of a two-sided container with a wall in between that has a hole in it, your gas molecule is kind of, hanging out here and it's flying around. It's going to just randomly knock into these walls. And then just by random chance, it'll eventually get through this hole, right? And so we want to know how quickly a gas might effuse or through this hole, right? And so one thing that you have to remember is that at the same temperature, what we just learned last lecture, the same temperature, a lighter gas moves faster, right? It has to in order to have the same amount of kinetic energy. And a faster molecule, if you think about kind of these random collisions, right? The faster you're moving, the more collisions you're going to make, and the more likely then you're going to be to get through this wall. So faster molecule, faster effusion. So at the end of the day, basically what you get is that the lighter molecule effuses faster. So what we can say is that the rate of effusion is inversely proportional to molar mass. Right? As molar mass gets bigger, effusion gets slower. As molar mass gets smaller, effusion gets faster. And there's actually an equation for this. I won't ever ask you to do this equation. It's not that important. Just know the basics. But you can actually find the molar mass of things. So you can say that the rate of effusion of gas 1 and put that equal to 1 over the square root of the molar mass, and then put the rate of effusion 2 under it, and then molar mass, the square root of the molar mass of the second gas up there. And then if you plug and chug, you can figure out molar masses of compounds. I won't really ask you to do these problems. I don't think they're that important. So effusion going through a small hole, that's like a balloon losing air, right? So one of these is helium, one of them is argon. Go ahead, take a second and think about which one is which, where it's going from left to right. Cool. So if you think about it a little bit, this one right here on the left is effusing faster. It's effusing faster because it's shrinking, so all the air is leaving it faster. And so we said one's helium, one's argon. So the one that's going to effuse faster is going to be the one with the smaller molar mass. Helium has the smaller molar mass, so this one will be helium, and then this one will be argon. Awesome, right? So Helium is lighter, so it's moving faster at the same temperature, right? They're both at room temperature, so it's more likely to leave. It's going to fuse faster. And that's pretty much it. Just know that the lighter molecule, it fuses faster.